Hello dear students, let us continue our discussion on the properties of the real number system. So in the last lecture we had seen that the set of real numbers together with these operations, that is addition, multiplication, it forms what is called a field. Okay. So that means R, the set of real numbers together with addition and multiplication, satisfies certain properties, okay, which we had listed. Okay, so these are actually called field axioms. Okay, field axioms. So these are the properties that we take for granted that yes, the real numbers satisfy those properties. Okay, and using those assumptions or using these properties, we try to derive other properties. Okay, so one of the properties that was listed was of course in my earlier lecture there was a mistake. By mistake, instead of writing existence of inverse, maybe I said inverse, but I forgot to write inverse. Okay, instead of writing inverse I just wrote existence of identity, so that's incorrect. Uddaluk had pointed this out, so thanks to Uddaluk. So please correct that also. It's existence of inverse, the fifth property, right? First one I had listed it as the sum of two real numbers is a real number, closure property. Okay, the second one was the commutative property, third one was associative property, fourth one was the existence of identity, and the fifth one was the existence of inverse. Each element in R has got an additive inverse. Okay, right? So for this existence of identity and existence of inverse, one question arises is about uniqueness. Okay, so in our axioms what we had listed was there exists an identity element. Okay, existence of identity, if you remember, we had listed this property as there exists an element, so we denote that element by 0 which is in R, such that a plus 0, this is always equal to a, which is equal to 0 plus a, and this happens for every a inside the set of real numbers. Okay, so this was the property that we had listed about existence of identity. Okay, now the question comes. So as of now you forget that whether you know 0 or not. Okay, suppose that you do not know what is 0. I don't have any idea about what is 0. Okay, and somebody gives me just this property that yes, R has got some element which we denote by this 0, and it satisfies that a plus 0 is a equal to 0 plus a for every a inside R. Okay, then he asks us that tell me whether this element 0 is unique. Okay, or can you find out any other element which also satisfies this property. Okay, right? So I told you we are listing out properties of R. Okay, the minimum properties of R which are necessary for our analysis purpose. Okay, so these are listed as properties, and every other thing is derived using these properties. Okay, so mathematicians, they listed these minimum number of properties which are required for studying the subject real analysis. Okay, so see, 0 has lots of other properties as well. A into 0 is equal to 0, means from our childhood we are doing those things. Okay, but that is not included in this field axiom. We will derive that as a property. Okay, using the other properties that are listed. Okay, so these properties are actually the most fundamental properties which are necessary to derive the others. Okay, so our question is whether the identity element or the 0 element in R is unique or not. Okay, are there any other element, or can there be any other real number which satisfies this? Okay, so when I make this type of statement here, we are not talking about uniqueness, we are just talking about existence. Okay, so this particular statement is just existence. There exists an element which satisfies this. Okay, it doesn't say anything about uniqueness. Okay, right? So this type of statement gives us existence of something. Okay, so existence doesn't automatically imply uniqueness. We will try to use these properties to show whether this uniqueness follows or not. Okay, so a zero element is unique. Okay, say here we can write it as a property. The additive identity in R is unique. Okay, so let us try to prove it, that there is only one such element which we can call as zero element. Okay, only one number will satisfy this particular property, right? Okay, so how to prove it? Okay. So the proof is this. Let me write it once again here. Okay, so this was the exercise. The additive identity or zero element, it is also called zero element, or the zero element in R is unique. Okay, so there is only one and only one zero element. Okay, so how we show this? Okay, so we will assume that zero comma, so let us take another symbol, say 0 bar belongs to R, be two zero elements. Okay, two identities, additive identities. Okay, suppose that there are two additive identities. Okay, suppose you find out one additive identity, your friend comes up with another additive identity. Okay, so both of you come to me to judge whether the identities that you have come up with are same or not. Okay, so remember what I need to prove. I need to prove that the additive identity is unique. Okay, so what does that mean? So whenever you have this type of questions in mathematics, okay, in most of the cases the solution is obtained this way. Suppose I want to show that something is unique. First we will assume that, okay, let us say that yeah, there are two such elements. Okay, then we try to prove that yeah, if that happens, then those two elements have to be equal. Okay, there is no other option. Okay, so if you come up with one zero element, your friend comes up with another zero element, ultimately I can show that yeah, both of you have got actually the same thing. Okay, so no need to argue, the zero element is unique. Okay, so this is what the procedure is. So assume that 0 bar belongs to R, B2 or R two additive identities. Okay, then by property of additive identity okay, we have 0 plus 0 bar, okay, will be equal to, so let us take 0 bar as additive identity. So if you look at this property here, the property that I told you, a plus 0, if 0 is the additive identity, okay, is additive identity, then a plus 0 equal to 0 plus a for every a inside R. Okay, so here by property of additive identity, by property, let us write it this way, by property of 0 bar as additive identity. Okay, so I have considered 0 and 0 bar as additive identities. So first let us use the fact that 0 bar is an additive identity. So that is why I have written, then by property of 0 bar as additive identity, we have, so since this is the additive identity we are talking about, so this any element. So this 0 here will now act as any element. So any element plus 0 bar will be equal to the element itself. Okay. So 0 plus 0 bar is same as 0, right? So let us write it as 1. Again, by property of 0 as additive identity. Okay, by property of 0 as additive identity. Okay, I can write it in reverse also, 0 bar plus 0, right? And by property of 0 as additive identity. So I am taking 0 as additive identity now, and 0 bar I will take it as A. So 0 bar plus 0 equal to 0 bar, which is equal to 0 plus 0 bar. Okay. So you compare 1 and 2. If you compare 1 and 2, you see here you have something called 0 plus 0 bar. In 2 also you have 0 plus 0 bar. Okay. You compare this. Here also you have 0 bar plus 0. Here also you have 0 plus bar plus 0. Okay. So ultimately what we can say is from 1 and 2, 0 and 0 bar are equal, right? Okay. Please have a look at this argument once again. I have taken, or I have assumed that 0 and 0 bar, they are two additive identities. Okay. Suppose you come up with an additive identity 0, your friend comes up with another additive identity 0 bar. Okay. Then what I do is I use the fact that, okay, first of all I accept that your friend has come up with a identity. Then 0 plus 0 bar will be equal to 0, right? Equal to 0 bar plus 0 by property of additive identity. Okay, this property, the property that I had already listed here. Okay. And next I assume that, or I use the fact that you have also come up with a 0 as additive identity. Okay, so I'll use that property, and in that case I'll use 0 bar as any element of R. So 0 bar plus 0 will be equal to 0 bar equal to 0 plus 0 bar, right? Okay, then just we can compare. Here you have this 0 plus 0 bar, here in this side you have 0 plus 0 bar. So from 1 and 2, actually 0 and 0 bar, they are the same thing. Okay, so from 1 and 2 and 2, we see that 0 equal to 0 bar. Thus additive identity is unique. Okay. Additive identity is unique. Okay. Right. So this is the proof. So since we have proved that additive identity is unique, so we can talk about, or whenever we write additive identity, we will just add the additive identity. Okay. So we will write 0 is the additive identity or 0 element in R. Okay, identity in R. Okay, so this the I can use only because we have proved that 0 is the only such element. Okay, so 0 is the only element which satisfies our property, right? Okay. Another thing which we can try proving is, see, in our usual mathematics, whenever you have this type of equation, say x plus a equal to a, so in the very next step what we do, we immediately write, means cancel a from both sides and write x equal to 0. Okay, there is also a fundamental property that we use, but means let me not say fundamental, obvious property that we use. Okay, so let us try to see that using the properties that we had listed, can we just say that, yeah, this is only the possibility, this is the only possibility. If there is an if an element x, if x and a are elements in R which satisfies x plus a equal to a, then in the next step immediately I can write x has to be the 0 element. Okay, it cannot be anything else, right? So this is also a sort of this uniqueness of additive identity type of thing. Okay, so let us try it, this exercise, or yeah. So if x comma a belongs to R such that x plus a equal to a, okay, then x has to be equal to 0. Okay, so this is show that. Okay, or let me write it as a result. Result. If x comma a are elements or are real numbers which satisfy x plus a equal to a, then x has to be equal to 0. Okay, so how we can write it? Okay, so this is one result which we will try to prove. Okay, right. So we can write this one as x plus a is equal to a. Okay, so what we can do is we can just use the property of this additive inverse. Okay, we can use properties of additive inverse. Okay, so given x comma or given x comma a inside R. Okay, so this will imply that minus a also is an element of R. Okay, of course minus x is also an element of R. Okay, but we need only minus a here. So it's given that, so minus a belongs to R. So now x plus a equal to a will imply that we can add minus a to both sides. Okay, so this equal to a plus minus a. Okay, oh sorry, I did not use the fact that yeah, so before proving this, let me just use or let me just first try that show the uniqueness of inverse element, that is additive inverse. Okay, that we have to show, so that we are comfortable or we can use this symbol minus a always. Okay, so the uniqueness of additive inverse, this was, yeah, we first established the basic fact that the elements 0 and 1 whose existence were asserted are in fact unique. Okay, so yeah, okay, so this 0 is unique, we already have seen, and additive inverse of each element is unique. Okay, so that also we can actually show, right? So exercise every element in R has a unique additive inverse. Additive inverse. Okay, so how do you show this? So let a belongs to R be any element. Okay, be any element. Okay, so what does our property say? By field axioms or by field axioms of R. Okay, so what does the field axiom say? One of the field axioms, for given any a inside R, there exists an element b inside R such that a plus b, this is equal to 0, equal to b plus a, right? This is what is happening, right, for additive inverse. So given any a in R, by field axiom there exists, field axiom gives us the existence of one b in R which satisfies this. Okay, now our this aim is to show that this is the only possible element, this b is the only possible element which satisfies this, no other element satisfies the same thing. Okay, so for that what I have to do, we assume that we assume there exists C inside R such that, okay, so we assume that, okay, there is another element C. Okay, then what is our intention? We will show that if somebody comes up with another element C which satisfies the same thing, I can immediately show that B and C have to be equal. Okay, so we assume there exists C in R such that A plus C equal to 0 equal to C plus A. Okay, then what I want to show? I want to show that this B and C are actually equal. So we have this, say, let us start with this A plus B equal to 0. So from here what I can do is I can add C to both sides, okay, because these two are equal elements. So writing A plus B plus C, this is same as writing 0 plus C, right? And here I can use the associative law. Okay, see how we are applying the axioms here. So A plus B plus C, oh sorry, no, I have to do it something different. I'll add C to the other side, okay, so that I can use this fact C plus A, right? So these two are equal elements, so I add C to the other side. So C plus A plus B equal to C plus 0, right? And then I can use the associative property here. C plus A plus B, this will be equal to C plus 0 is C by property. Okay, so this by associative property, associative or associativity of addition, and by, so, and in the right side we have applied the property of additive identity. Okay, by property of additive identity. Okay, additive identity, right? So in the next step, if we see, so let me do it here itself so that we don't miss out. So in the next step what we are doing is this, just one more two lines. So from here we'll get C plus A. So C plus A, you see what is C plus A? C plus A is given to be 0. So I can write this one as 0 plus B is equal to C. But what is 0 plus B? 0 plus B is again B is equal to C, right? So if there is an element C which satisfies the similar things, then immediately I can show that B and C are actually equal. Okay, so identity or inverse, so additive inverse of each A inside R is unique. Okay, there is only one additive inverse, okay, is unique. So using this fact, using the fact that additive inverse is unique, we note that additive inverse, so we can talk of the additive inverse. Okay, so since additive inverse is unique, additive inverse is unique, so for any A inside R, it's the unique additive inverse of A is denoted by minus A. Okay, so one is an element in R, so its additive inverse is denoted by minus 1. Okay, so 2 is an element in R, right? Its additive inverse is minus 2. Okay, so there is only one additive inverse for each element. Okay, so this is what, right? So we denote additive inverse by minus A. Okay, so now we can come to that problem exercise. If x comma A is in R with and x plus A is equal to A, then x has to be the 0 element. Okay, x has to be 0 only. Okay, so this solution we can do, we can start with, say, x plus A equal to A, So of course, without using the uniqueness of additive inverse also, we can do it, because A belongs to R, so there exists an element B which satisfies this. Okay, so let us do it that way only. So since this one is given this, so since A belongs to R, so there exists an element B inside R such that A plus B equal to 0 equal to B plus A, right? So x plus A equal to A will imply that, so what I do is I add B to both sides. Okay, so x plus A plus B will be equal to A plus B, and then again I use the associative property, x plus A plus B will be equal to A plus B. But what is A plus B? A plus B is given to be 0, means A plus B is 0 because A is an element in R, so there exists an element B which satisfies this. So x plus 0, this is equal to 0. But what is x plus 0? X plus 0 is x, so x is nothing but 0. Okay, so this is also actually the uniqueness of additive identity. Okay, so if there is an element which when added to any other element A gives us the element A itself, then that element has to be equal to 0. Okay, so this is another way of saying that additive identity is unique. Okay, of course you can do it this way also, given that x plus A equal to A. So since A belongs to R, so minus A belongs to R satisfies A plus minus A equal to 0 equal to minus A plus A. Okay, so therefore x plus A equal to A will imply that x plus A, so what you do is you add minus A to both sides, so this is equal to A plus minus A, right? A plus minus A, and then I can just use associative property. So this is x plus A plus minus A, this is equal to 0. So from here also x plus 0 equal to 0. So there are several ways of doing it, so x has to be 0, right? So whenever we get this type of expression, x plus A equal to A, immediately we can write x is equal to 0, right? Okay, and another one is that let me show, that is the left cancellation law, right cancellation law. Okay, in R the cancellation laws hold, cancellation laws hold, okay, for addition. Okay, hold for addition. So for multiplication we have a different result. So in R the cancellation law laws hold. What are those? A plus B equal to A plus C implies so for A, B, C inside R, if A plus B equal to B plus C, A plus B equal to A plus C will always imply that B equal to C. Okay, so this also from our childhood we have been doing something like this, x plus 2 equal to x plus y. Okay, so we cancel x on both sides and write 2 equal to y. Okay, so this is basically the cancellation law. So since we have not listed this as a fundamental property, we will try to see whether, or we will try to prove that yeah, this is actually satisfied by using the properties that we have listed. Okay, by only by using those properties we can show that yeah, cancellation law actually holds. Okay, so what we are doing basically is that you might be wondering why we are doing these obvious things. These are not actually obvious. We are trying to develop a theory. For the time being you forget that you know anything about this cancellation law, that x plus 2 equal to x plus y implies 2 equal to y, you can cancel x on both sides. You for the time being, temporarily you forget that yeah, you do not know this. Okay, what you try to understand is yeah, we have a set which satisfies these properties. Now let us see whether these things are true or not. Okay, that is how the real analysis is being developed. Okay, right. So we are giving a formal structure to whatever we have learned till now. We are trying to analyze, yeah, satisfy ourselves, yeah, actually these things are true if we assume this 10 properties or 10 field axioms. Okay, so that is the thing. So if a, b, c are any real numbers which satisfy a plus b equal to a plus c, then immediately we can cancel a on both sides and write b equal to c. Okay, so how do you do it? Given a plus b equal to a plus c. Okay, so this is already given to us, right? So what we can do is we can just use the fact that this element a has its additive inverse, right? So since a belongs to R, so its additive inverse, additive inverse, okay, minus a also belongs to R, okay, and so a plus b equal to a plus c, this will imply, so what we do is we add minus a on both sides, okay, we can do that. Minus a we are adding on both sides because a plus c and a plus b, they are same elements, and then what we do, we apply the associative property, okay. So that is why this associative property is very important. If we do not have that property, then see we cannot conclude anything, right? So minus a plus b will be equal to minus a plus c, okay, right? We have the associative property, so immediately we can separate this. But what is minus a plus a? This is actually 0. So 0 plus b equal to 0 plus c, right? So what is 0 plus b? This is equal to b and this is equal to c. So when you write these things in exam, so please make sure that you list out the properties as well. Okay, so here actually I have used here actually I have used the associative property, associativity of addition, okay, of plus. Here I have used the property of additive identity, okay, additive identity, right? So these things I have used here. Okay, so the cancellation laws hold. So one of the cancellation law is this is called the left cancellation law, and another one is the right cancellation law. If you have something like b plus a equal to c plus a, this will always imply b equal to c, okay. So what in this case, how to prove it? We add minus 1 to the right side, okay, right? Here we have added minus a to the left side. So here in the second case we'll add minus a to the right side, okay, and then we can show it, right? So cancellation laws hold. Now we are satisfied that yeah, in fact what we are doing is it follows from this three properties. See, three properties we have used: associativity of addition, property of additive identity, okay, and existence of additive inverse, okay. So this see how this, why these properties have been listed as field axioms or fundamental, very fundamental properties, okay, because using these we can derive so many other properties, okay, right? So next is I want to show that the element 1 is unique, okay. The multiplicative identity or unit element, unity in R is unique, okay, is unique. That is our uniqueness of multiplicative identity, multiplicative identity. So there is only one element which when multiplied by any other element gives that element itself, okay. Multiplicative identity is unique, in R, okay. So how do you show this? So if we have this one, so let 1 comma 1 bar, okay, 1 is the thing that is given by the field axiom, that there is an element 1 which satisfies, and let us take say somebody else comes up with another this element 1, okay. So this proof also will do it very similar to whatever we had done, right? So one of the property is the element 1. So let a 1 and comma 1 bar be two unity elements, okay, or multiplicative identities, multiplicative identities. this. Then by property of 1 as multiplicative identity, okay, we have, so if I use 1 as so if you remember, the property of multiplicative identity was 1 into a equal to a into 1 for all a inside the set of real numbers. Okay, so here if we use 1 as multiplicative identity, then 1 into 1 bar, this should be equal to 1 bar equal to 1 bar into 1. Okay, right? So this is 1, and again by property of 1 bar as multiplicative identity, okay, 1 bar multiplied with 1, this will be equal to 1 itself, equal to 1 dot 1 bar. Okay, so this is 2. So by 1 and 2, you see this element is here also, this element is here also. Okay, so similarly this element is here, this element is here. So by 1 and 2, this 1 is actually equal to 1 bar. Okay, so there is only one element which acts as multiplicative identity. Okay, so of course very similar to this, there is this exercise as well, is given in bottle and sherbet. If u and say b not equal to 0 are elements in R with u into b equal to b, right? B is a non-zero element. Okay, then this u has to be, then u is actually equal to 1, right? So this is another property. If we have an element u which when multiplied by another element b gives the element b itself, then this u has to be 1 only. Okay, right? So how do I prove it using this properties? Okay, so here you see we require another property of the field axiom, that is the multiplicative inverse property. Okay, existence of reciprocals of multiplicative inverse. Okay, so we have u dot b equal to b. Okay, this is given, and since b not equal to 0, this is also given, b is a non-zero element. Okay, so since b not equal to 0, so by field axioms, so in one of the field axioms, you see there is a field axiom called existence of multiplicative inverse. Okay, so every non-zero element in R has a multiplicative inverse, right? So by field axioms, there exist element C inside R such that B dot C is equal to 1 equal to C dot B. Okay, right? So this is given. Okay, so there is an element C which actually satisfies this. Okay, then so we have u dot, it is given to us that u dot b equal to b. From here it will imply that see, I want to use this property somewhere. Okay, so what I do is I multiply both sides by c. So what this is u dot b dot c, this will be equal to b dot c. Okay, next I use what? Associative law of multiplication. Okay, so this was also listed as one of the field axioms. You see the necessity comes here. Yeah, if I want to show this result, then I have to use the associative property of multiplication. Okay, so but b dot c is 1 by our this thing. So this is actually u dot 1, b dot c is again 1, so u dot 1 equal to 1. But by property of this additive so multiplicative identity. What is u dot 1? U dot 1 is nothing but u. So this is u equal to 1. Okay. So that is the thing. Yeah. Okay. So it is given to us that u dot b equal to b. So what we do is by field axioms there exists an element c inside R which satisfies this. B dot c equal to 1 equal to c dot b. Right. So we use this. And of course you can write this c as 1 by b. But I prefer not to write it because let us do it independently instead of assuming that the inverse element is unique. Okay. So what we have shown is the multiplicative identity is unique, and what else we have shown is if there is an element u, means if there is an equation of this type u dot b equal to b, then where b is non-zero, then b can be cancelled out. Okay, and we can write that u is equal to 1. Okay, so this is another property that we have done. Okay, so let us do this property also, the multiplicative any non-zero element, any non-zero number in R has unique multiplicative inverse. Okay, multiplicative inverse. Okay, so this is the last result we are doing. In the next lecture we'll see. Okay, so let A belongs to R and A is not equal to 0. Okay, so then by field axioms there exists an element B inside R such that A into B equal to 1 equal to B into A. Okay, also let there exist C inside R which satisfies such that A into C equal to, means there is an element, another element which satisfies the same thing. Okay, what I have to show? I have to show that B and C are actually equal. Okay, so now A dot B equal to 1. So what I do again, I apply that this associative rule here. So what we do is we multiply both sides by C. So this is C dot A dot B. This will be equal to C dot 1. So here we have C dot A. Here I apply associative property. C dot A dot B equal to C dot 1 is actually C by property of this multiplicative identity. And C dot 1 here we have already listed. C dot 1 is 1. So this is 1 dot B equal to C. But 1 dot B is actually B. So this implies B equal to C. So please keep on writing these things, these properties what we are using. Okay, these are very important. So here this is associativity of multiplication. Okay, multiplication. Right, you write it properly. So here we see that multiplicative inverse in R is actually unique. Okay, so because of this uniqueness of multiplicative inverse, we write multiplicative inverse of A, multiplicative inverse of 0 not equal to A in R. Okay, inverse of this, let me write it this way, of A in R with A non-zero is written as 1 by B. Okay, sorry, 1 by A. Right, the multiplicative inverse of A is denoted as 1 divided by A. Okay, so this is the thing. Say for example 2 multiplicative inverse is half. 2 by 3 multiplicative inverse is 1 divided by 2 by 3. Okay, of course that comes out to be 3 by 2 by our usual notation. Okay, but here in analysis you will see very rarely we will use this 2 half, 2 by 3. Almost we will work the entire analysis with symbols only. Okay, A, B, U, okay, like that. So that is why the symbolical notations are necessary here, right? So we have proved the existence of uniqueness of multiplicative inverse as well. Okay, so all these are required. So till now we have not used distributive property anywhere. So in the next lecture you will see where we are going to use the distributive property as well. Okay, right? So let me give you an exercise which you may try. Show that if A is an element in R then a dot 0 is always equal to 0. Okay, a multiplied with 0 is always 0. Okay, so or the other way, if I write the same problem, show that a dot 0 equal to 0 for all a inside R. Okay, so see, this we had not listed as a field axiom. Okay, in field axiom we have not listed this anywhere. Okay, so but we will try to show this, that any element multiplied with 0 element, okay, gives 0 only. Okay, right. So since our school days we had this notion, or we learned it by heart, that 0 multiplied with anything else gives us 0. Okay, so how formally it happens, if we define 0 as an this additive identity, then this property naturally follows. Okay, so see, we have just used one single property of 0, that 0 added with, means we have just assumed one single property of 0, that 0 added with any other element gives the element itself. Okay, and with that property we are deriving all the properties of 0. Okay, that is why axioms are necessary. We have not listed this property as a separate property. Okay, because it's not necessary, we can derive it from the others. Okay, but say associative property, we have to list it. We cannot derive it from say commutative property. It's not possible. Okay, right. So these are natural, we have to accept that, right? Okay, so in the next lecture we'll continue.